For the binary tree, okay. Binary tree, as you know, we have left and right. And there is the ADT, the abstract data type. The binary tree ADT extends the tree ADT. So that is, it inherits all the methods of the tree ADT. Still remember the tree ADT? Okay. It was before the midterm. Maybe you almost forget everything. So here, yeah, we have the basic function, like what is the element is equal to or not equal to the node. Okay. And then we have whether it is root or not. And I want to know what is the parent, how many children do we have, and then it is children, or if it is the children, then we want to make the iteration for each of the child. And then I want to know how many of the nodes, and then whether it is root, it is leaf, or it is empty. Okay. So this is the abstract tree class, and we can extend it to the binary tree. If you still remember in the object-oriented, okay, we have the, if you still remember at the time, we have one example about student. And then we have one more class about graduate student. So the graduate student inherit every method, every data in the student. We have the graduate student. The only difference is, for example, the number of credits. The number of credits for the graduate students is about 30 credits, but the undergraduate students should take about 140 credits. And yeah, that is only the difference. But other things is similar, like the student name. They have the name, they have the student ID, they have the address, they have the cell phone, and etc. This is also the case. We have the tree ADT, and we have the binary tree ADT. And most of the function in the binary tree inherits from the tree. There are some additional methods. We want to know what is in the left and what is in the right, and whether they are sibling or not. You know, sibling. So if it is sibling, means they are in the same level. We can update methods. So update methods may be defined by the data structure implementing the binary tree. When we deal with the binary tree, there is also the traversal method. Previously, we used the pre-order and post-order. Pre-order, traversal, post-order, traversal. But in the binary tree, yeah, we have another traversal, and the first traversal, we call it in-order traversal. In-order traversal, it means a node is visited after its left subtree and before its right subtree. I guess the idea is similar with the post order. we will do from the most left and then go and find the other left and go to find another left and then go to the right. So the idea is similar with the post order. In this case, we have the in order. First, we will check if V has a left child. So the first, we will check if there is a left child, then in order left V. We call again here and then check if V has a left child. Okay, it has the left child. Then in order left of V. So we call again. V has a left child. Is there any left child? No. Then we visit. So now we visit the node. After we visit the node, and we need to check if V has a right child. Is there any right child? No. Then it returns back to the parent. And after it returns back to the parent, then we will visit. This is number 2. And V has a right child. Yes, it has a right child. Then we call in order right V. When we call in order right V, then again we will check if V has a left child. Has a left child? Has a left child here? Yes. Then again we will do the in order left V. Has a left child? No. Then visit. So we visit this. And we will check has a right child? No. Then it return back to the parent. And so on. So this is the pseudocode. We can do with the arithmetic expression. If you still remember, we can use the arithmetic expression with the binary tree. And we can extend the idea using parentheses. Using parentheses. You know that in the programming, there is a precedence order. Multiply, division is higher than the plus and minus. So in some cases, we need to make the parenthesis. So how we apply this parenthesis? Then we can have a specialization of an in-order traversal. It means when you do with the in-order traversal, you will add more statements. In this case, this is the print expression. We have the left child. This is the question from the in-order traversal. And then we add one more statement to print the parenthesis. And then we just do recursion. And then we have another statement to print the element. And then we will check if it is right child. We will check the left, the right one, and then we will print another parenthesis. Okay. So this is the specialization. So I guess when you do your final, your team project, okay, if you have something like searching or maybe you want to use this kind of expression with this in order traversal, you can make your own specialization function. So this is the specialization function for arithmetic expression. So before we first we will check, is there any left child? Yes. Then we will print the parenthesis. Is there any left child? Yes. Then we will print another parenthesis. And then after we print the parenthesis 2 times, so we print the element, which is 2. And so on. So the order is the same with what we learned from the tree before. We can also deal with the post-order traversal. We call this is the specialization of the post-order traversal. The recursive method returning the value of the subtree. And when visiting an internal node, combine the values of the subtree. If we use this function, we want to print the expression. We just print the expression. For this one, we want to evaluate the arithmetic expression. So at the end, I want to know what is the result. In this case, we can use the post-order traversal. Yeah, the idea is the same with the post-order traversal. Before, we have 2 multiplied by 5 minus 1 plus 3 multiplied by 2. So if it is leaf, then return the v dot element. If not leaf, then x will be the evaluate expression left v, and then y will be the evaluate expression of right v, and then this will be the operator, and we can return what is the result based on the x operator y. There is another kind of traversal, we call it Euler tour. In the Euler tour traversal is the generic traversal of binary tree. It's more general, and it includes a special cases of pre-order, post-order, and in-order traversal. So this is a walk around of the tree and visit its node 3 times. So this is the idea of visiting the node for several times, but we can visit the edge, or this is the line, okay, for 1 time. So every of this node will be visited at least 3 times, but between the nodes will be visited 1 time. For example, like this one. From plus, it goes to multiply. So there will be 1 time only. And then from multiply, it goes to 2. So it's 1 time. From 2, it returns back to the multiply. It is 1 time. From multiply, it goes to the minus, it is 1 time. Minus goes to 5, 1 time, and so on. So it means this Euler tool will visit all the nodes 1 time until it finishes. We call this is the Euler tool, and it is a combination of the pre-order, in-order, and post-order. So this is the very special case of the traversal. We can also use this kind of trees for the link. If you still remember, we have the link this. So the link structure for trees, we want to find what is the element and what is the parent node and what is the sequence of the children nodes. If we have the node like this one, I have the root, which is B. I have the child A and F and D, and I want to have this as a sequence. I would like to start from A and then D and then F. For the D, I have another children, C and E. And the first node is, yeah, we have, this is the element. Okay. And then this meaning the, oops, this meaning the parent. What does it mean by this symbol? This symbol means nothing. Okay. There is no parent. If there is no parent, it means this is the root. Okay. And then I want to know the sequence of children nodes. So I have this next as a sequence. We have 3 children. The first will go to this node. The second will go to this node. And the last will go to this node. It is linked to this node. And in this node, we have another 3 elements. Sorry, we can have the storing object with the elements, parent node, and the sequence. So this element is A. And what is the parent? We put the link to B because the parent of A is B. This is D, and we link to B because the parent of D is B. We have F, and we link F to B because the parent of F is B. For A, it is empty. No children. No children. For D, there is a sequence of children, and we go to C and we go to E. Again, this is the element C, and we have the C linked to D because D is the parent of C, and E has a link to D because the parent of E is D. Okay. So this meaning the link structure. If it is the tree, we know that we can have many children. We can have many parents. How about if it is binary tree? binary tree, we have a specific conditions. We have only right and left. Okay. Then we need to define what is the element and what is the parent node and what is the left child node and what is the right child node. So the link structure will be, if, for example, if like this one, we need to understand what is the position. So in this case, we have the B as the element of this node, no parent, because B is the root, there is no parent. And then the left node will go to this, and the right node will go to this one. And then we have, this is the element of A, and the node A has link to B. The node D has link to B. And this is D. There is no left node, there is no right node. For the D, we have C as the left, and then we have E as the right. Okay. This is only the visualization to show how the node link to each other. Later, you need to use the code to understand where is the position of this node. We can make using array for the binary trees. And if we make arrays, of course, you need to understand the index of the array. I want to make the tree, or I want to make the binary tree using array. So we call it this is an array-based representation. I have this tree. How can I put this tree into an array? Okay, so nodes are stored in an array A. How we can put every of these elements into the array? There is a way, we call it, this is using rank. How we can start this one? Let's suppose this is an array, index 0, index 1, index 2, index 3, and so on. Okay, at the beginning, we have index 0, index 1, index 2, index 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. Node P is stored at A, rank V. What does it mean by rank of V? First time, rank root equals to 1. Rank of the root equals to 1. Then we will put A into the array index 1. It means I will put A here. If node is the left child of the parent node, then the rank node will be 2 multiplied by the rank parent node. What does it mean? There is a node there is a node B which is left. If it is the left child, then the rank of the node B will be 2 multiplied by the rank parent node. What is the parent of B? The parent of B is A. So what is rank of A? Rank of A is 1. So 2 multiply 1. Then the rank of B is 2. It means I will put B into the index 2. Now, I check if the node is in the right child of the parent, then rank of the node will be 2 multiplied by the rank parent node plus 1. So I have the rank C, which is 2 multiplied by the rank of the parent node. What is the rank of the parent node? It is rank A. And it will be multiplied by 1 and plus 1. That's correct. Good. Okay, then it will be 3. I will put D in the index 3. Okay, let's do one more or 2 more examples. I have E. What is rank E? We have to multiply by the rank parent node. So it means the rank B. Rank B is 2. Then it will be 4. So I will put in index 4. So this 0, 1, 2, 3, 4. So in index 4, it is E. Okay. And then let's say I have rank C. Rank C is in the left. Because it is in the left, then we will use this formula. Multiply by rank parent node. The rank parent node is 3. So 2 multiplied by 3, it is 6. So we will put C on the 6. Okay. What about F? We will put on the F here, and then J we will put in the index 7. 5, 6, 7. Okay.
In your third case, easy.
Oh, same. This one, D. Okay, thank you for your corrections. Oh, D. Yeah, this is D. Okay. Thank you. So this is the left. This is the right. Okay. So if it is in the right side, then it will be 2 multiplied by the rank of the parent plus 1. So for example, rank J. What is rank J? It is 2 multiplied by the rank of the parent node, which is 3 plus 1. So it is 7. Okay. Now my questions. Where is the index 8, 9? Then it will be empty. Okay, why? Because there is no child node of E. In that case, you will have 8, 9 is empty, and then 10, 11 with G and it's like this one. Is it okay? Of course it is okay. Okay. Yeah, we don't need to fill every position on the array. Okay. Oh, this finished. Any questions? No questions? Then let me continue to the next. I already uploaded more PowerPoint files to the e-class. The next, what I want to explain is about the priority queue. The priority queue, it is the very common sense. If we use the queue, then there will be a priority queue. So we will check what is the priority queue and then sequence-based priority queue and the priority queue sorting. In the priority queues, it means in every of our life, we will have our own priority. Priority means, I don't know what is the Korean. Okay. We want to see a collection of items where the item is a pair of key and value. I have key, I have value, and I can add the key and value. Key k and x is the value, and I will remove min. It means I will remove the smallest key. There will be some additional methods. Let's say I want to see minimum. It means I will just return but does not remove an item with the smallest key. And I want to know the length of the priority queue, and I want to check whether the queue is empty or not. Yeah, there are many applications. For example, standby flyers, okay, or auctions. You know auctions. Yeah, if you let's say go to auctions, you want to sell some products. The product will be sold to some people who can give higher price. Okay. So if you have higher price, then you will have more priority. Something like that. In the stock, yeah, in the stock also, if you want to buy some stocks, so if you buy more lots, yeah, then you will have more priority other than the other customers. And this kind of queue depends on the key. maybe in the real life situation, for example, if you are going to a queue and there will be a priority for children, okay, for example, or if you are in the queue, there will be a priority for example, disabled person, 장애인. Okay. Then we can give a small number. If it is a small number, then it will be the priority. So let's say I put the P, the first P is empty. And then I will put the 5. 5 means, yeah, any number that is the item of A can be added into the queue. And then I have a next item, it is C, and I put the number 9. So it means it is not the priority. It can be later. So I have 5A, 9C. I have a new item B, and okay, I know that this one should be in the first. So I give a smaller number, which is 3. So the sequence will be 3B, 5A, and 9C. And I have another item, which is D. Okay, this item is 7, because maybe this should be done before the last one, but yeah, it's not that important to be the first. So maybe it is, yeah, on the position of 7. So I can check what is the minimum. Okay, the minimum is 3, P. If I want to remove the minimum, means, yeah, I want to serve. Yeah, like in the queue, you know that if we want to remove, it means the person will go to the server, or the person will get the service. So I will remove the 3B. So we have the remaining items, 5A, 7D, and 9C. If I want to remove again the minimum, then I will remove the 5A. And if I want to check the length, then there are 2. If I want to remove the minimum, 7D, I want to remove the minimum, it is 9C. And if I check is empty, yes, it is true. And if I want to remove the minimum, it is error. Okay. In this kind of problems, we have the total order relations. What does it mean by total order relation? The total order relation means I have the order. The keys in the priority queue can be arbitrary objects. The key here, like 5, 9, 3, 7, it can be arbitrary objects. Arbitrary objects, it means, yeah, it can be numbers, it can be alphabet, like A, B, C, D, or maybe A, B, C, D with big letter, or A, B, C, D with small letter. Yeah, it can be arbitrary object. 2 distinct entries in priority queue can have the same key. So for example, there are 2 children. Okay. The first key is using number 3, and then I put A, the child A, and then another children named B is also using the same key. So yeah, in this case, we have the 3, A and 3, B. So what is the total order relation? The total order relation means we have the concept of this one, less than or equal to. Reflexive properties. The meaning by reflexive property means if the x is less than equals to x. So in this case, we have the same. Yeah, 3 and 3. So they are the same. Anti-symmetric properties. Anti-symmetric properties means if x is less than equal to y and y is less than equal to x, then x equal to y. And we have another properties, transitive properties. In the transitive properties, if x is less than y and y is less than equal to z, then x is less than equal to z. Okay, so this is what we call as the total order relation. In the way to deal with the priority queue, one item, okay, we call it an item in the priority queue is simply key value pair. Key is the k and value is the v, or in the previous one we call it x. Okay. Priority queue store items to allow for efficient insertion and removal based on keys. So I have the class priority queue. This is the base. And then I have another class item to store the key and value. So the constructor will have two members, k and v, key and value. And then I would like to check later whether the key is less than, or this is less than. Okay. And we have the is empty, whether the priority queue is empty or not. Oh, only this one. Okay, this is on the base. Okay. Actually, we can have a lot of other methods. Okay. Now the issue will be how we can implement the priority queue. There are two kinds of ways to implement the priority queue. First, we can just do the implementation with unsorted list. What does it mean? When we have 4, okay, maybe this is the key. Okay, the key is 4. And then there is another key. There is another item, enter. So it's 5. And then there is another key, so 2. There is another key, it's 3. There's another key, 1. So it is similar with Q. Whenever you have another item or whenever you have a new node, then it will be added in the last one. The performance of this one, it takes O1 time, since we can insert the item at the beginning or at the end of the sequence. So insertion at the end, it is O1. However, you know that the priority queue, we need to remove the minimum. After we have 4, 5, 2, 3, 1. If I want to remove the minimum, then I need to sort. Okay. If I insert it with the unsorted list, if I want to remove the minimum, it means I need to find the minimum first. After I found the minimum, then I can remove it. So the worst case, to find the minimum, it takes O n time. Since we have to traverse the entire sequence to find the smallest key. However, we can also do the implementation with sorted list. The sorted list means if I enter 4, okay, I will put 4. If I have 5, okay, I will check the sequence. I will sort it first. Okay, 4 is first and next is 5. And then I will insert 2. So what is 2? Oh, 2 should be in the first before 4. Then I will do the sorting and then I will have like 2, 4, and 5. And then I have 3. So I will do the sorting 2 and then 3 and then 4 and then 5. I have 1. Then I will have 1 and then I have 2 and then I have 3, 4, and 5. So in this case, the performance will take O(n) times for adding, because every time I add, it should be sorted. And the remove and the minimum will take O(n) because it is already sorted. Okay. Okay, I guess this is the time to stop. Any questions?